important to me that Rust helps people generally feel welcome and included, no matter what kind of person you are, what kind of group you're from. And those already are some very laudable goals of Rust. But I want to go into a few more that are also really important. Rust guarantees stability. So when you upgrade Rust, your code will keep working. This is a really important property for people because it, again, means in general you can fearlessly upgrade Rust. You can move to a newer version, and you're not going to be unpleasantly surprised of, oh, I have to do some extra porting work to move my code forward to the next version. It tends to just always work, and if it doesn't, that's a terrible bug, and we try to fix that as quickly as possible. And then on top of that, another property we don't talk about a lot is that we really are building a language that intends to last the test of time. So what we mean by that is that we want Rust to keep thriving many decades from now, not just be a language that's here for now and then expects to be replaced by a successor in the future, or voluntarily or otherwise. We really do want to keep moving Rust and evolving Rust to keep up with people's needs. So decades, that's really quite a long time in computing terms. So what would Rust look like in 2050? It's incredibly far off in computing terms. Well, first of all, the obvious question to talk about if you're talking about computing in 2050 is, well, will we have solved the AI alignment problem yet? And either we will have, in which case we can just ask the computer to write whatever the current language is for us and then sit back and relax, or we won't have, in which case gray goo doesn't write programs and we'll have bigger problems. But let's not talk about that one for now. I'm sure that there's plenty going on in the AI forums elsewhere talking about AI. So let's talk about the parts that's within scope for us. So this is a good time for me to give some important disclaimers about the talk. First of all, the goal of this talk is fundamentally to inspire what Rust could be and how much Rust might change or stay the same in decades to come. It's not necessarily to lay out a perfect roadmap for exactly what's going to happen. So anything I'm talking about that isn't written down in one of the consensus roadmaps for the project is absolutely wild speculation on my part, and you should take that as inspiration and definitely not any kind of commitment on behalf of Rust. So, as I said, I'll be speculating very heavily. And most importantly, really, nobody speaks for all of Rust. Doesn't matter if you're a leader of the project, a developer of the project, or just a random contributor. Everybody has an opportunity to change Rust, to influence Rust, but no one person speaks for it. And it's a consensus open source project, and we sometimes change our minds. Anything that hasn't shipped in stable Rust is subject to change. So, with all of that out of the way, what would Rust look like in 2050? Well, there's a few important questions we could ask about that. First of all, what's going to change about Rust? Second of all, what's going to stay the same in Rust? What's going to feel the same even in decades from now? And are we going to have one Rust in 2050? Or are we going to have dialects and variations on Rust? So let's talk about Rust stability guarantee again for a moment, because if you're talking about lasting the test of time and being around in 2050, well, I still expect Rust to be stable by that point. Rust 2050 should still run Rust 2018 code or 2015 code. So one of the things that makes this incredibly feasible and possible to imagine doing is the mechanism for additions. And I honestly think this is one of the most important things that we've created in Rust next to ownership and borrowing. Additions are a mechanism we have for updating Rust without breaking existing code. What this means is that we can say, okay, Rust 2024 is a language that looks a lot like Rust 2021. It has this handful of changes, like a couple of new keywords or a slight tweak to syntax here. Here are the rules for migrating from 2021 to 2024. And if you want, you can keep writing Rust 2021 code, or 2018 code, or 2015 code, also known as Rust 1.0. And you can even mix these in the same program. So when you talk about what Rust's most unique and important language feature, well, most people will say ownership, borrowing, and lifetimes. This is the foundation of its safety and security properties. This is what is improving the stability and security of Rust programs. This is also the thing that takes people the most time to wrap their heads around, the most unique concept. So I don't think there's much arguing that this is one of the most unique features of Rust. But what's the most important feature for the evolution and maintainability of Rust long term? I would genuinely say additions. And I have not seen the like of this in many other languages, though I have seen some signs that some languages are starting to look at this as a possibility to adapt from. So right now, we currently have 3 additions and we're on the cusp of a 4th. We have 2015, also known as 1.0. We have 2018, which introduced a bunch of changes like the new module system, not to mention the addition mechanism in the first place. We have 2021, which was mostly a few minor cleanups. And then we have Rust 2024 coming a year from now, which should have a few nice new features. So if we're talking about Rust in 2050, where are we going to be? We're going to have 12 approximately Rust editions, one every 3 years or so, where we haven't fully committed at this point to a once every 3-year cadence, but everybody has so much expectation that that's what's going to happen, that it seems likely that that's what's going to happen. And we'll be, again, 1 year off from putting out a 13th edition. Hopefully it'll still be an auspicious one. That is a lot of versions of Rust. That's really quite a different thing from saying, oh, we have 3 editions and here's how they vary. We're going to have 12 on the cusp of 13 editions. And on top of that, there's some really interesting bits of added complexity. Rust editions not only let you mix a Rust 2015 crate with a Rust 2018 crate with a Rust 2021 crate so that your libraries don't all have to move at the same time you do, which that's already an improvement over, like, if you see additions and you think, oh, well, what about C99, C11, C23? You can pass a flag to the compiler to do a different version of the language. But then all the header files that you include in that C file are parsed using that version of the C language, which means if you want to move forward to C 2023, if there's any incompatibility whatsoever, then every header file that you work with in every library that you use has to be compatible with that. Whereas in a Rust edition, if you move forward to Rust 2024 and your dependency is still on 2021, no problem. But on top of that, your dependency can define macros, and then you can expand those macros in your crate. And vice versa, you could depend on something that moves forward to 2024 and you're still on Rust 2018, and it can define macros and you can expand those in your crate and it still works. Rust's concept of which edition you're in isn't just based on what crate you're in, it's what crate did the span of this code expand from, and there's logic in the compiler to handle that. So this means it's amazingly easy to mix code between editions without any trouble, which is why we can upgrade so easily. It also adds a huge amount of additional complexity to the compiler. And as a result of that, we could ask, well, are we still going to have in 2050 support for every edition directly in Rust C? Now, I definitely said, and I stand by, we're going to have support for Rust 2015 code in Rust C in 2050. But would we have that directly in the Rust compiler? Would we have some translator that you can run that's a pre-processor pass that turns your 2015 code into Rust 2051 code? Will we have a stable ABI and a mechanism for saying, well, here's the snapshot of the old version of the compiler that you used to compile that code? I don't think that last one's very likely. I think the translator possibility is possibly what we might do for maintenance. I don't know at this point. But one way or another, we're going to keep that stability, and that's going to be an added source of maintenance complexity over time. So let's take a look at a few languages that have already stood the test of time and see what we can learn from those about how much they've changed and how much they've stayed the same. So first, let's start with something venerable and respectable. We've got C. We've got C++, we've got Java and JavaScript, we've got Perl and Python, all the variations on Lisp and Scheme. There are ML variants, there are Haskell variants. All of these are 25-plus-year-old languages. And there are others. If I've missed your favorite language here, then I'm sorry that this slide had to fit on a single screen. But like in general, it's a much shorter list than all the languages out there. The ones that are 25 years old and still getting actively used and exciting people in various ways, or dreading people in various ways and causing them to have maintenance issues. One way or another, they're still alive and kicking. So let's talk about some of these languages. How much have they changed over time? Well, let's start by looking at C. We had a language pre-C89 and NCC where types were more like guidelines than actual rules. And we went from there to a language that now has simple type inference, at least within a single line, that has attributes you can attach to statements and functions, that has really simple type-based dispatch that's kind of, you know, languages first generics. You have Boolean types, you have compound type literals and structures, you can do declarations of variables anywhere, you have type of, you have finally guarantees that the machine you're running on is a 2's complement machine, and you can make that assumption. This is a lot of evolution for a language that started out with ambitions of this is a smarter macro assembler. And yet, if you look at C today, it still pretty much feels like C, just better. You can look at C++, and this may be a bit of the odd language out in this list, because you went from a language that was kind of C with classes enhanced to modern C++, which is trying very hard to be a safer language, as long as you can all agree on which subset of the language is modern C++ and which subset isn't. But the language has actually evolved a lot more than other languages on this list. The syntax is still the same. The character of writing the code has actually drastically changed in a lot of ways for many people. If you look at something like JavaScript and the evolution of that from the early scripting of the web to the current language people use, we've introduced strict mode. We have real variable declarations and real constant declarations, lambdas and closures with simple syntax, promises and asynchronous code, modules and the ability to import them, generators, iterators, destructuring assignments, template string literals, all sorts of simple error handling and error propagation mechanisms. It is a substantially evolved language, and yet I'd still argue it's still pretty much the character of JavaScript. It still feels like this language that started out to script the web and glue things together. You look at something like Python, over time, it's grown list comprehensions, generators, unified types where you can build more types exactly like the built-in ones and inherit from the built-in ones, with statements and contexts to take and remove resources, full Unicode support, meta classes, all sorts of interesting things you can work with. And, you know, to acknowledge the elephant-sized Python in the room, there was Python 3, which is not quite the same language. And despite the compatibility break, I would still say current Python feels remarkably like some of the very early Usenet era Python, like this feels like pseudocode that happens to be executable. It kept the character of Python. So let's talk about Rust for a minute. Well, pre 1.0, we made some really important changes that made Rust interesting and stand out and worth looking at. We took out type sigils so that it looked a lot less like Perl, looked a lot more like a more modern language. We took out the runtime, and that alone was one of the most incredible changes pre 1.0 that made this not just another language with a runtime, but made this a language that, again, can go anywhere C can go and do anything you might want it to do. We added the distinction between stable and nightly so that we could evolve features and only expose the ones we're ready to commit to stability of on the stable compiler. And post 1.0, we had some amazingly huge changes. Question mark was not in Rust 1.0. It was introduced dozens of versions later. It is to this day one of the most controversial RFCs in Rust's history. Now, syntactically, you see it multiple times per line in Rust and makes Rust so much less verbose than it otherwise would have been. Additions, as I already mentioned, constant evaluation that is getting more and more capable. The ability to derive traits, to automatically generate code in a convenient way to glue things together. Asynchronous programming and native support for that. Non-lexical lifetimes, a so much better borrow checker that it made it much less common that you write code and then spend more time fighting the borrow checker to convince Rust that it's right. Generalized, generic associated types, GATs. I mentioned this one because it really fills in a corner of the language and the type system to make two of Rust's larger features work together. This is a fairly notable evolution in its type system. And there are other changes where that came from that change the syntax of Rust, change the usage of Rust, and don't change the fundamental character of Rust. Despite some pretty major changes, most of these still feel like the language that they started out like. Most of them kept the same character, the same principles, the same values, and the people who developed in them originally, if they looked at the code today without, having all of the intervening steps, they'd probably be surprised at a syntactic level, and at the same time it's like, okay, I see the language that I started out with in here somewhere. This doesn't feel like it's utterly alien to me. So in the same way, Rust 2051 is still going to feel like Rust, the language. It'll still have much of the same character, but it's likely to have evolved quite heavily in that time. And if you jumped from today to 2051 and looked at that code without seeing any of the intermediate versions of Rust, you might be surprised at how much has changed, but you'd still say, hey, the language that I knew and loved is in here. And I would also say it will have evolved by listening to its users. We don't change Rust for the sake of changing Rust. We change Rust for the sake of helping to meet the needs of users. So some of the things we're likely to have changed. We're likely to have another round of NLL or Polonius introduced into the language where the borrow checker is understanding your code so much better. We're likely to make more steps toward orthogonality, where if a feature works somewhere in Rust, it should work everywhere in Rust that feature makes sense rather than having special cases. We're likely to have automatic references where you don't have to say, oh, this is a number, but I have to use a reference because this function needs it to be a reference. We'll figure that out for you and try to have lints so that you catch potential issues. We're likely to have generators to make iterators and async iterators so much easier to write. Having built-in async traits, a built-in async runtime so that you don't feel like you have to start out making a choice you don't have the knowledge to make yet of what do I use. Just async that just works without ecosystem splits. The standard library is likely to still be making fairly conservative choices in 2051. There's a lot of people who talk about, like in Python, there's a standard piece of wisdom. The standard library is where code goes to die because people go use things from the ecosystem and not what's in the standard library. We try very carefully to avoid that and be very conservative in what we pull in. But at the same time, the standard library is also going to be a lot less special in 2051. A lot of the things it can do, anybody could build in the ecosystem, and it'll be easier to either rebuild the standard library or build your own standard library and glue it to Rust very easily. We're likely to have addition mechanisms for libraries, including the standard library itself, so that it can move forward without breaking any compatibility. This is going to be a lot harder than the language because people have to interoperate between versions of Rust, but we still need some mechanism for that evolution. We're likely to make it possible for anyone with any library crate to take advantage of stable versus nightly markers and say, well, here's something I'm experimenting with, but I'm not committing to it in the SymVer of my library. We'll have sandboxing for build.rs, for proc macros, not just for security purposes and safety purposes, but so that Rust just understands everything that went into your build, can rebuild faster and not be unaware of what on your system you depended on. We'll have support for multiple code generation backends. LLVM, GCC, the crane lift backend, GPU backends, possibly native Rust things we don't even know about yet. We'll almost certainly have first-class support for non-CPU targets in Rust, things like GPUs, FPGAs. We'll have code generation for platforms that may not even exist today. We're very likely to end up with a cross-version stable ABI. Amani is working on that. We will have a subset of Rust features that are supported across versions of the Rust compiler based heavily on Dyn and Dyn traits and trait objects, very inspired by the Swift stable ABI style. We're likely to have some kind of capabilities system to let you choose between different functionality as a backend for a similar common interface, whether this is an async trait or an async runtime, or what you want your file system and networking in the standard library to be based on. Imagine sandboxing your networking while using things that look like standard library calls. So I finally want to touch on, will we have one version of Rust, or will we have many dialects of Rust? So what do I mean by a dialect? Well, historically, the language team guidance from Rust has been we don't want to create dialects of Rust, which means we don't want to have different people writing different, not fully compatible subsets of Rust. And a big reason we say that is whether you use a feature or not, you're going to be reading other people's code. And if there are features that your dialect doesn't use, well, you'll read other people's code and you'll still need to understand those features. That means we don't want to have lints or warnings about standard language features, like, oh, I want to opt out of letting you use this language feature, because whether you do that in your code base or not, you're still going to have to understand that feature in other people's code bases. So another way of saying this is, if we want to evolve the Rust language, we have additions for that, and we'll evolve the language together rather than in many splintered directions. So we definitely don't want to have dialects of Rust. And wait, who put that there? We kind of have dialects of Rust. We have 2015, 2018, 21. Well, okay, that's all right, because we encourage people to move forward to the current one together. And the old versions are there for compatibility. So we don't really expect that people are going to need to go read 2015 code every day in 2051. So, okay, fine, we have this one mechanism for dialect. Okay, who put that one there? We have cases where people don't necessarily fully understand unsafe code just because they're writing safe Rust code. And not everybody dives into all of the depths of writing unsafe Rust. So in a way, this is a language that has some extra features that you don't use in other contexts that some people are more expert in than others. We have embedded and no standard, where all of a sudden you don't have all the same library features you're used to. You don't have anything you didn't bring with you. We have async, which the famous, what color is your function? How can you mix these things together? What do you write in async that you don't write in sync? And oh, don't put your sync code in the middle of your async. So we do actually have some things that have people writing very different Rust languages within Rust, and that increases the surface area of Rust for everyone. These in particular, we felt like, okay, it's worth it. These are really important things, but we really want to limit the number of those that we do. But at the same time, there are some other areas where we might genuinely want to introduce dialect-like things in the language. What would it look like if we did? Well, imagine if we wanted quick and dirty prototyping in Rust. Imagine if you wanted to be able to write a script, not by pulling out Python or another rapid prototyping language, which it's a great language, but this is an area that Rust is notoriously not great at. And some of the things we could introduce for that would be more aggressive type inference, things like inferring function arguments or doing abstract interpretation to muddle along and say, well, it's a member of a trait, and there's only this one thing that's a member of that trait. Let's muddle on and see if the code makes sense until we need to execute it. We could imagine that, well, we might not have to get all the borrow checking right because the user could just implicitly wrap everything in reference counting and locks and have a pseudo garbage collector. We could even have a real garbage collector. And then scripts have this tendency to evolve into programs. And when you do a quick and dirty hack, well, there's nothing quite as permanent as a temporary hack. So you might copy that into a program, and maybe you want to start maintaining that as a longer-term program. So imagine if you could just have a lint that's on for programs and off for scripts, and it has Rust fix support and cargo fix support, and all of a sudden all those types that Rust inferred for you more aggressively that might not be long-term stable to infer, we plug into your code, add them automatically, and now your program is more maintainable, a little more verbose, but it's actually really valid Rust. It would be a dialect. It might actually provide a lot of value. This is the kind of thing we could consider doing. So, wrapping things up, Rust is a language that we want to last for decades, and we have every intention of making that happen. Rust 2051 is still going to be Rust. It's still going to feel like Rust. It's going to be your Rust because we're going to evolve it to meet the needs of you and many other Rust users. So what do you want the language to be? Work with us, tell us what it needs, and Rust 2051 is going to evolve in directions that you, among others, will help to shape. With that, I'm available online by email, by Fediverse handle, social.joshtriplet.org. I'm available on GitHub, and I'm building all sorts of advanced build systems on buildit.dev. Thank you very much for your time, and if you have any questions, please feel free.
Thank you, Josh. Please stay for QA session. 30 years later, I can still confidently review the Rust code I wrote this year.
Say again, please.
30 years later, I can still review my Rust code I wrote this year.
Absolutely, yes. I very much hope that in 30 years, you'll not only be able to read other people's Rust code, you'll still be able to read your own. Though in 30 years, some of us might need eyeglasses for that.
OK， 行，大家线上有什么问题啊？可以举手提问。可以。OK。
I know Hugging Face is using a lot of Rust in their AI infrastructure and software. So, will there be any better support for AI in Rust? Yeah.
So, will there be better support for AI in Rust? I know that there are a lot of people working on that and making use of Rust, not just for glue and underlying layers for AI, but trying to add some of the higher level code and inference directly in Rust. There's been a lot of interest in things like differentiable functions in Rust. So I expect that with the number of people pushing in that direction, that we're very likely to add features both for better implementation of pieces of AI as well as better support for using Rust to help to train and infer with AI. Any other questions?
Yeah.
Hey, sorry, I just be late. We've got a session this afternoon talking about if Rust is going to challenge C in operating system. So, what's your perspective on that?
Bring it on. In all seriousness, I think it's not so much is Rust going to as how much more is Rust going to. People are already building operating systems in Rust, and people are adding Rust to all of the most popular operating systems at this point. Microsoft is writing drivers and subsystems in Rust in Windows. Linux has support now for writing drivers in Windows. Writing drivers in Rust, and one of the first such drivers is a GPU driver, famously a complex thing to write. So at this point, I think that we are likely to continue to see Rust following the same patterns of incrementally replacing C in places where it is feasible to do so, and not just wholesale replacing C, but being able to incrementally go within the programs that already have C in them and just replace more and more until at some point, well, hey, let's replace the rest, and now we have something written in Rust. How quickly that'll happen? Well, I'm a big proponent of there's no fundamental reason to rewrite something that's working, so I expect that it will evolve over time with some big jumps as people get excited. But I think it's already happening at this point that people are writing major system level functionality ranging from firmware, BIOS, UEFI, up through drivers, operating systems, file systems, disk drivers, virtual machines, user space, low-level daemons, everything all the way up is already getting Rust added to it. And rather than looking at it as, oh, here's a brand new project in this space that's completely written in Rust, which does happen sometimes, there's going to be a lot of, oh, hey, how'd that Rust get there? And it's a language that's easy to add a little of and then add more as you get more excited about it.
All right, so so from what you see currently, is that just a kind of open source behaviors, or is there any big players in the industry? As you said, that just the firmware level, the UEFI, the BMC, probably any one of those big players in the real industry, you're aware of that's playing a big role in pushing this forward?
I think there's going to be a lot of both. On the one hand, there's a lot of open source folks who are not worried too much about product timelines or the cost of a rewrite, and they're just excited about using Rust in more places or gluing things together more easily. And on the other hand, there's a lot of very big players who are starting their new projects in Rust, using Rust inside their company, and encouraging writing new subsystems in Linux and Windows and other OSs in Rust. Partly because they're just tired of dealing with security holes, tired of doing non-fearless programming and being less productive. I think genuinely people are pushing it forward for good reason, whether you're backed by a product timeline and revenue or just excitement and fun.
Okay. Once again, thank you, Josh. Please stay back your seat.